Linear approximations come up later as well. But to help you understand the idea of why we even use linear approximations, I wanted to graph, for example, if you kind of skip down to look at example 1, we're going to be finding a linear approximation for the function f of x equals square root of x at a equals 1, and a is the x value. So I'll show this up here. If you want to follow along on your graphing calculator, you can. I am going to graph the square root of x, which I already have it typed in.
Jared, did you forget a graphing calculator?
And actually, so graph the square root of x, but I'm going to shorten the window. So on the window, because I'm focusing this around the x value 1, I'm going to do, well, actually, no, just kidding. I'll do that later. Square root of x, standard window. Sorry. And this, like I said, I'm showing it up here if you wanted to follow along. What I want you to notice, though, is the square root of x, you know, is a curve, correct? It's not linear. Would you all agree? It's not a line. Now, if I focus around the x value 1, so I'm going to restrict my window to, I'm going to do my x min as 0 and my x max as 2. I'm not going to change the scale. And then the same for the y's, I'm going to do 0 to 2. So I still have a square viewing window. So 0 to 2 and 0 to 2. So I just restricted the window. But on that screen, would you agree that you can still see that the function is a curve? Okay. I'm going to now zoom in on the curve where the x value is 1. So if you go to your zoom options and you just choose option 2 where it says zoom in, mine comes up automatically. Does your cursor, it should probably come up in the center of your screen. So does yours come up at 1, 1 on the curve? Okay, leave it there and just hit enter.
Whoa.
Okay, now if you just saw this graph, notice you could go to the window and see what the scale is, but if I just gave you this graph, would you say this looks like a curve or a line, just by glancing at it? It looks fairly linear. So, and we're not even zoomed in as close as we could be. We could zoom in even more. I think if I hit enter again, will it zoom again? Yes. So I just hit enter again. My cursor was still at 1, 1. Now I'd say it looks even more linear. You could go to your window and see how small of a window your calculator has created. When it's graphing. Okay, but this is so you understand what a linear approximation is. What this is saying is if you have a curve, if you are very, very close on the curve to the x value, that the curve is approximately equal to its tangent line. So if I graphed a tangent line at the x value 1, and this curve at the same time, and I zoomed in really, really close, you would barely be able to tell what was the tangent line and what was the curve. The tangent line can be used as an approximation to a curve, as long as you are close enough. So this is just showing if you zoom in really, really close to a point on a curve will appear linear. So you can use a tangent line to approximate. This is typically used if you don't have an equation for a function. So the first example we're going to go through, I realize we have things to talk about above, but the first example we're going to go through, you do have the equation of a function. That's to, again, give you the idea of what this is used for, how to create it. but it's typically used if you don't have the equation of a function and you're trying to predict other values that aren't given to you. This is saying you can use the tangent line as a prediction equation of sorts. So that is the idea that is stated above, so I don't need to reread through this. This is for your reference, but basically saying if it's difficult or impossible to approximate a value for a function, possibly because you're not given the equation, you can use the tangent line. So this is talking about some vocabulary, but I guess what I really want you to focus on is linear approximations are the tangent lines. So yes, it's referred to as something different. There's a different name for it, but the linear approximation is the tangent line. So you'll see that as we go through this. This section is still finding equations and using tangent lines. So it says we use the tangent line at the point A, f of A, as an approximation to a curve y equals f of x when x is near A. So if you have the equation, or rather I want to write the formula for the equation of a tangent line to a curve y equals f of x at A, f of A. To write the equation of a line, you need a slope and a point. We have a point. How do you find the slope of the tangent line? The formula thing, which is what?
F of x, f of A plus A minus f of all the x. The quantity of
the limit of that, which I heard somebody else say one word. That starts with a D. Derivative, yes. So the derivative of f at A is the slope, because the derivative is that same limit. So the slope to any curve at a point AF of A is going to be f prime of A. So if I use f prime of A as the slope, and then here's my point, I could write it in point slope form. So y minus the y coordinate is f of A equals the slope is f prime of A times the quantity x minus A. Okay, so yes, I realize we're writing a formula, but it's not a different formula than we've used before. It's just kind of generalizing. And we are building so you know what linear approximation and linearization mean as well. What you are going to see, though, is in this case, when we get down to linearization, you are solving this for y. So I'm going to add f of A to the other side and write it this way. Oops, not equals. So I'm just adding that f of A to the other side in front of the f prime of A times the quantity x minus A, because like I said, with linearization, you are going to want to get the y alone. So this is what we would refer to as the equation of the tangent line for any function f of x at the point A, f of A. So then when you are talking about a linear approximation, which is also referred to as a tangent line approximation, what this is saying is that the curve, the original curve you're starting with, is approximately equal to your tangent line at the x value A. Morgan? Yes, ultimately, I just wasn't trying to include like the A, f of A, and then the slope in an equation, but you're probably going to be solving this to get it into slope-intercept anyway. Yes, but this was just a rearrangement to show kind of going from point slope to go to a different form. So this isn't a formula that you have to use. I'm trying to stress it's still the tangent line. So if you're using slope-intercept form, that's fine. So the linear approximation, again, is saying the curve is approximately equal to the tangent line, again, as long as you're close to that A value. So our original curve would be whatever function f of x you're given. is approximately equal to your tangent line equation, which from above we wrote that as f of a plus f prime of a times the quantity x minus a. So what you're going to see if you're asked for a linear approximation is this is how they're going to want you to answer it. Whatever your curve is approximately equal to whatever your tangent line equation is that you would get. And then the linearization is written differently from the linear approximation. This is actually the linear function whose graph is the tangent line, and it's noted with L of x for linearization. So this would just be L of x equals your tangent line equation. So L of x would equal your f of a plus f prime of a times the quantity x minus a, or if you have it in slope-intercept form. So we could also say up above that this really means f of x, your original curve, is approximately equal to L of x, and L of x is your linearization or your tangent line. So I know this tends to be a theme in calculus. Here's another way to ask you to find the tangent line. That's basically what this is. When you're asked to find the linearization, that's the same as being asked to find a tangent line. But you have to know that. L of x it just represents the linearization. So if they ask you for a linearization, it is just the tangent line, but they use L of x instead of y. All right, so here's an example. So it says find the linear approximation for the function f of x equals square root of x at a equals 1. So linear approximation, we're looking for this. We're looking to say the square root of x approximately equals your tangent line equation. So you first have to find the equation of the tangent line. And we know in order to find the equation of a tangent line, you need the slope of the tangent line, which is the derivative. So we're going to need to find, I'll find f prime of x and then substitute 1 in at the end. If you wanted to substitute 1 into your limit right away for a, you could do that. I'll just write the formula here. Limit as h approaches 0 of f of x plus h minus f of x all over h. And our function is square root of x. So f of x plus h is the square root of x plus h minus f of x is the square root of x all over h. And how do you evaluate that limit? Yes, multiply by the conjugate. So square root of x plus h plus the square root of x. And remember, this is on top. It's really FOILed, although your outer and inside terms will cancel out. And then don't distribute on the bottom. Just leave it in factor form. You're only trying to simplify the top. So square root of x plus h times itself would just be x plus h. And then we'd have a negative square root of x and a positive square root of x, and that would be minus x. And then the denominator, I'm going to leave the h factored out. Oh, I forgot to rewrite my limit as h approaches 0 in front of that. Okay, and then on the top, your x's cancel. And then rather than rewriting this, not trying to lose anybody, but you can see all you're going to have left on the top is h, and that's going to cancel with the h on the bottom. So your numerator is now just going to be 1. And if you replace the h in the denominator now with 0, that's the only remaining h, you'd have 1 over the square root of x plus the square root of x, which is 1 over 2 square root of x. That's your derivative. Questions there? Okay. So then the slope of our tangent line is going to be f prime of, our a value is 1. So substituting 1 into our derivative. So 1 over 2 times the square root of 1, so just 1/2. And to write the equation of a line, you need a slope, and then you also need a point. We know our x value is 1. What would our y value be? Or how would we find our y value? Yep, it's also 1. Plug it into the original function. Square root of 1 is 1. So our point is 1, 1. So then to write our tangent line, I'm going to start with point slope and then just solve it for y. So we would have y minus 1 equals 1/2 times the quantity x minus 1. So then we would have y equals 1/2 x, and we would have a negative 1/2. Adding the 1 then would give us a positive 1/2 or 0.5 for our b value. So when you solve it, I realize this is how we wrote it up here because I wanted to keep the f prime in there and everything. But really, when you're solving it, you're probably going to write it in slope-intercept. Just it's easier if it's fully simplified in this case. Okay, so we're not done. Yes, Lydia. You don't have to, no. If you added the 1 and said 1 plus 1/2 times this quantity, that's fine. Yep, you just want to get y alone. Once you have the tangent line, so now the linear approximation, again, that's saying that your curve is approximately equal to your tangent line. So the linear approximation says that the square root of x, because that's our original function, is approximately equal to what we got for our tangent line, which is 1/2 times x plus 1/2. So this would be the linear approximation. The curve is approximately equal to the tangent line. Questions? All right, so here's how this is used. In part B, it now says use the linear approximation to approximate these 3 numbers. So again, the next example we're going to go through, we don't actually know what the equation of the function is because I realize you could just type this in your calculator. I get that. This is getting you the idea of how to use this. So we're approximating these values, and then we're going to figure out, are these approximations overestimates or underestimates? So to use the linear approximation, I'm just going to rewrite that down here. One thing to notice is that all 3 of those values, the 0.99, the 1.01, the 1.05, these are all numbers that are close to your a value of 1. So that's the whole idea of this, as long as your x values are close to your a value, you can use the tangent line to approximate the values of the function. So rather than plugging these numbers into the original function, because again, we're going to pretend we don't know what the function is, we're plugging these numbers into our tangent line equation to get an approximation. So we're saying the square root of 0.99 is approximately equal to, so notice 0.99 is x, 1/2 times 0.99 plus 1/2. And you're evaluating, I didn't need that parenthesis there, but you're evaluating the linear function at 0.99. So if I take in my calculator 1/2 times 0.99 plus 1/2, this is saying the square root of 0.99 is approximately, I did not put that in there. Should be approximately 0.995. So that would be the approximate value for this based on our linear, or based on our tangent line, our linear approximation. Liz? So that's where this example is getting you the idea for how to use this. These are typically used when you don't know what your function is. So I know in this example, I know that we know f of x, but it's getting you the idea. You'll see in the next example, we're going to have a function where we don't know the original function, so we can't just plug it in. So we're using the tangent line to approximate the values because we don't know the function. But yes, I realize in this case, you could just type in square root of 0.99. This is just getting you to understand the idea of how to use these. Kai, did you have a question? No, because here your x value is still 0.99. This is just saying you're approximating this value. So we're approximating, this is saying we're approximating the curve square root of x with this line. So we're approximating the square root of 0.99 by plugging 0.99 into the line. Does that make sense? Okay, so then if we did that for 1.01 and 1.05, so 1.01 would be approximately 1.005, and then 1.05 is approximately 1.025. So these would be your approximate values based on the linear approximation. Okay, so again, typically these are used if you don't know the original function. I realize here that we do. Are there questions, other questions on how we did this? That'll be example 2. So we will go through that because that's a good question. Okay, so then there's another part to this question though. It says, are these approximations overestimates or underestimates? Did any of you actually type these numbers in to see what they really are? Okay, were these lower or higher than the actual? They were higher. So these are overestimates. Now, the question then will be, if we aren't able to plug them into the original function because we don't know what it is, how do we know if they're over or underestimates? So another way to think about this is if you graphed the original curve, or if you weren't given the function, you plotted whatever you were given to figure out what the curve would look like. But if we actually look at the graph of the square root of x, so I'm going to graph square root of x, and I'm going to graph the tangent line equation, so the 1/2 x plus 1/2 on the same screen. I'm just going to do the standard window. But as you graph that, is the tangent line, actually I should probably zoom in towards 1, 1. I'll go back to my window of 0 to 2. So when you're close to 1, you're looking to see is the tangent line above or below the curve. So right now, is this tangent line, it's touching the curve at 1, 1. Is it, like aside from that point, is it above or below? It's above, meaning all of your y values on your line are greater than the y values on your curve. So therefore, they're going to be overestimates. Because these 3 values are values on the line, not the actual curve itself. But again, it's an approximation. So that's a way to figure out over or underestimate estimates is think about, is the tangent line above or below your curve? we're going to look at example 2 because then maybe this will tie it together. Now you know what to do. Here's where you would more likely use it when you don't actually know the function. So this is very fitting because Thanksgiving is next week. Suppose that after you stuff a turkey, its temperature is 50 degrees Fahrenheit, and you then put it in a 325 degree Fahrenheit oven. After 1 hour, the meat thermometer indicates the temperature of the turkey is 93 degrees Fahrenheit, and after 2 hours, it indicates it's 129. Predict the temperature of the turkey after 3 hours. Okay, we don't have an equation for a function here. So we're going to have capital T represent the temperature, and then lowercase t represent the time in hours. So we could pick out 3 ordered pairs from what we're given. We know the initial temperature of the turkey is 50 degrees Fahrenheit. So at time 0, the temperature is 50 degrees. We know after 1 hour, it is 93. And after 2 hours, it is 129. Okay, but we don't actually have an equation for the function. We are not expected to find an equation for the function. So you're not typing this in your calculator and doing a regression. That's not expected, and you should not do that. So to predict the temperature of the turkey, though, after 3 hours, we can use a linear approximation to the t-value 2 because that's the closest t-value to 3. So to find the linear approximation at t equals 2, we go through the same process we just did in example 1. We need to write the equation of the tangent line. And to do that, we need a slope. And to get a slope, we need a derivative. So we need to find what t prime of 2 would be approximately. How do you find a derivative from a table of values? Right, and we've always used 1 on either side. The closest one on either side, that's the same distance. Now, if you don't have another value on one side, the closest approximation you can get is the slope between the value itself and the one closest to it on the one side you do have. Okay, you're not making up values here. You just use what you're given. That's the closest we can get. So t prime of 2 would be approximately 129 minus 93 over 2 minus 1. So that would be 36. 36 over 1, so 36. Yes, it would be degrees Fahrenheit per hour if you had to label it. So we have, and this would be our slope. So for our tangent line, we know our slope is 36. Our point is at the t-value 2, so our point is 2, 129. So we can write this, and I need to remember to not use y's and x's. I'm going to use the t's. So I have capital T minus 129 equals, the slope is 36, times the quantity lowercase t minus 2. And then t minus 129 equals 36t minus 72. Add 129 to each side. Should be 57 plus 57. Okay, that's your tangent line. So for the linear approximation, again, your curve is approximately equal to your tangent line. So if I wanted to find t of 3, this is approximately going to equal if I substitute 3 into my linear equation here. So approximately going to equal 36 times 3 plus 57. And that would be 165 degrees Fahrenheit. So after 3 hours, our linear approximation says this will be the temperature of the turkey. Again, approximately. All right, questions on that? Yes. The T of 3. Oh, like this would be the value on the actual curve itself for the function, and then this is the value of the tangent line at 3. So the value of the curve at 3 is approximately equal to the value of the tangent line at 3. Yep. It doesn't ask you this in the problem, but just so you're able to figure it out, any ideas on whether or not this would be an overestimate or an underestimate? Or how would you figure it out? You are using data points below 2, but that wouldn't be, if it was under, that wouldn't be the reason why. So you're looking at like, these are all going up by 1s. So this difference is 43, and this distance was 36. So, yep, T is an increasing function. The temperature is going up, but at a decreasing rate. So the temperature went up more in that first hour than it did in the second hour. So the curve, we're going to be looking at this more next week. The curve for T would look something like that. So it's increasing, but it increases more at the beginning, and then it starts to increase at a smaller rate. And so the tangent line to any point on this curve is going to be above the curve. So this is an overestimate. Questions on that? Okay.